Hi Rockridge, this is Mrs. Berger, and today we are going to run through the concepts that were included in our project-based learning unit, Unit 5A. This was on polynomials, characteristics of polynomials. We worked a lot in Desmos. We created roller coasters. So this is for you if you missed the majority of the project days, or if you didn't do so well on the assessment and need to retake it, you'll be running through these notes. So let's dive right in. So we saw a lot of patterns as we were looking at the different behaviors and the different characteristics of the polynomials. So I want to put that into chart form so that you can get a sense of where those patterns come from. So this chart's going to help us understand degree, leading coefficient, and end behavior of polynomials. So we have talked about end behavior before. We looked at the right and left sides of the graph and talked about whether on the left it was going up or down, and on the right it was going up or down. So same concept here. We'll just have some different things happening with different degrees. Let's start with linear. You know what a linear function looks like. That could be something that looks like this: y equals ax plus b, right? And so the degree of this polynomial is 1. The power on x is 1. That little thing that I circled just there. So this little power is an invisible 1. That's why it's a degree 1. The highest power on the x is the degree. The leading coefficient on this one, we're going to pretend like a is a positive number. That's what this means. A greater than 0 means the leading coefficient is positive. So whatever number's sitting in front of there, it's positive. And when you have a positive a for lines, a positive slope for lines, we know that they look like this, right? The end behavior for that on the left, as x goes to negative infinity, the f of x goes down to negative infinity. And on the right, as x goes to positive infinity, f of x goes to positive infinity. Hopefully that's fairly obvious. If I'm going too fast, go back and play that part again. Similarly, if we have, and let me start calling these f of x. If we have f of x equals ax plus b linear, still a degree of 1, still a little invisible power of 1 here. But let's pretend like that a in front of the x, the leading coefficient, is less than 0, or a negative number. We know that if a was a negative number, you would have a falling line, right? And that would mean that the end behavior on the left was going up and on the right was going down. All right, we've also talked about quadratics. We know what those look like. Here's an example. F of x equals, or standard form, ax squared plus bx plus c. Now we have an x with a higher power. The highest power there, the highest power of the polynomial is going to be your degree. And in a quadratic sense, the highest degree is 2. When you have a quadratic in which a, the leading coefficient, is greater than 0, or positive, so positive, this was negative, this was positive. So a greater than 0 is just another way of saying positive leading coefficient. When that happened, when we had a positive leading coefficient, we knew that the shape of that quadratic was like this, right? It could be skinnier, it could be wider, but it generally looked like that, right? It was up, up on the ends, up, up. And so on the left side, it was up to positive infinity, and on the right side, it was up to positive infinity, right? Similarly, when we had f of x equals ax squared plus bx plus c, still a degree of 2, right? Highest power listed there on the x's was at 2. But when the leading coefficient was negative, when a was less than 0, we knew that that produced an upside down u, right? A parabola that was upside down. And so the end on that was down to negative infinity, down to negative infinity. We talked a little bit about cubics as well. We didn't dive quite so deep into them, but we looked at cubics, and we knew that the standard form for a cubic is ax cubed plus bx squared plus cx plus d, right? The highest power listed there being a 3. So if that's true, we have a degree 3 polynomial. When the leading coefficient, the number glued to the front of the highest powered x, is greater than 0 or positive, we know that that looks kind of like that. It might be a little higher on the turns, but kind of like that. It could have been up and down and up. But something that looked like that was what was produced by that, when there was a positive leading coefficient on a cubic. So the end behavior on both of those is down on the left and up on the right. Similarly, if we had a cubic, ax cubed plus bx squared plus cx plus d. Same thing, degree 3. But now if that leading coefficient, if that a that's glued to the front, whatever number that is, that's glued to the front of x cubed is a negative number or less than 0, we know that that produces something that looks like this, or something that looks like, something that looks like this. And that is up on the left and down on the right. Now, we've never talked about them, but quartics, that's what we call a degree 4. You can imagine what those look like. F of x equals ax to the 4th plus bx to the 3rd plus cx squared plus dx plus e, right? And all of those letters are all just numbers of some kind. They might even be 0, but all of those numbers are numbers of, all those letters are numbers of some kind. And when we have a degree 4, a leading coefficient that's positive, whatever number a is a positive number, that, let me tell you, looks something like this. It would look like this, or possibly like this. And what can we say about the end behavior on that? It's up on the left and up on the right. And you can certainly play around with this on your calculator or on Desmos as well, the graphing calculator on Desmos. When we have a quartic or a degree 4 that has a negative leading coefficient, or an a number that is a negative number, less than 0, still a degree 4, nothing changes, but we have a negative leading coefficient, that, let me tell you, looks like this, or possibly like that. And we know that that is down on the left and down on the right. So we've talked about linears, quadratics, and cubics before. I just talked to you about quartics. Take a look at this chart here that we just filled in and see if you can see a pattern. See if you can see a pattern in the end behavior. See if you can see a pattern based on the degree and leading coefficient. Can you make a determination about the shape? Can you make a determination about the end behavior? Can you see a pattern here? One pattern you might notice is something we call turns. Something we call turns. The number of turns in a graph, if you add 1 to that number of turns in a graph, you can come up with a degree. Let me show you. Let me work bottom to top on this one. So take a look at the number of turns here. Take a look at the number of terms on this quartic. I turn here, I turn here, and I turn here. I turn 3 times. Turning means instead of going increasing, I flip down to decreasing, or I flip from decreasing to increasing. That's what I mean by turns. So on this quartic I just circled in yellow here, we turned 3 times. We had 3 turns. 3 turns produces a degree of 4. Same thing here. 1, 2, 3 turns. 3 turns produces a degree of 4. 2 turns, turn here and turn here, turn here, turn here. 2 turns causes a degree of 3. 1, 2 turns, 1, 2 turns. 2 turns produces a degree of 3. 1 turn, 1 turn, 1 turn, produces a degree of 2. 0 turns, nothing in a line, right? It's forever increasing or forever decreasing, so there's no switching direction. No turns, or 0 turns, produces a degree of 1. So what pattern did you see just come forth here? If I count the number of turns in my shape and add 1 to it, I'll have the degree of my polynomial. So that's certainly a pattern that many saw throughout the project. They started seeing that pattern emerge. Another pattern you might see is related to the degree and the leading coefficient and how that causes certain end behavior. An even degree, 2, 4, 6, 8, etc. An even degree and a positive leading coefficient causes shapes like this. So degree 2, degree 4, degree 6, 1, 2, 3, 4, 5 turns. That produces shapes like that. What do you see that are all true of all of those? Even degrees, positive leading coefficients cause end behaviors of up, up. You can always count on that. That will always be true. You can visually look at a graph, see that the algebra, see that it has an even degree and a leading coefficient that's positive, and it will be up on its ends. If the degree is even, 2, 4, 6, 8, etc., and the leading coefficient is negative, or a is less than 0, you will see this happen. 1, 2, 3, 4, 5, 6. You will see down, down, and you should have seen that up here in this table for all the evens, 2s and 4s. This will always be true. Even degrees will match on the ends, and if they match up, they have a positive leading coefficient, and if they match down, down, they have a negative leading coefficient. And again, many saw that pattern emerge as they were doing their project. Degrees that are odd, and when we say odd, of course, we mean 1, 3, 5, 7, etc., with a leading coefficient that is positive, look like this. A line looks like that. A cubic might look like that. Let me count my turns. 1, 2, 3, 4, 5, 6. Oops, sorry. Try that one more time. 1, 2, 3, 4, 5. 1, 2, 3, 4. So 4 turns cause a degree 5. What do we notice about the ends for an odd degree and a positive leading coefficient? We are down on the left and up on the right. Let's take a look at odd degree with negative leading coefficient. So 1, 3, 5, 7, any of those degrees with a negative leading coefficient. The front number is a negative number. Looks like this. Here's a negative line, a negative cubic. We can go on forever. But anything with an odd degree, the highest power is an odd number, and it has a leading coefficient with a negative number, acts like this. It's up on the left and down on the right. That's a pattern that many saw as their projects played out. So when you look at a graph, you can immediately tell not only the end behavior, but also the degree, whether it's even or odd, and the leading coefficient, whether it's positive or negative. And that is what you'll be asked to do on the assessment, is to look at the shape of the graph and determine if the degree is even or odd, and what degree it is, and whether the leading coefficient is positive or negative. This is a summary of what we just talked about. There's really no notes to take here. The even degree polynomial, we can remember that the ends act like a quadratic. The most simple even degree polynomial is a power of 2. So it's quadratics, which we're very familiar with. So up if it's got a leading coefficient that's positive, down if it's a leading coefficient negative. Odd degree polynomials act like lines or cubics. Lines and cubics are the simplest forms of odd degree polynomials. They're down on the left, up on the right for positive leading coefficient, and they're up on the left, down on the right for negative leading coefficient. And of course, this summary right here is just what we said out loud. So that's 2 pages of notes that can kind of get you whatever you need to memorize about how these things work or reason out how these work. So we just talked about degree, leading coefficient, and end behavior. So let's switch now to our discussion of, let's practice. Let's try this practice. So go ahead and pause the video. Fill in, for these polynomials, fill in the leading coefficient, what that number is, whether it's positive or negative. Fill in the end behavior, and just sketch the general shape. It doesn't have to be perfect, but sketch the general shape. Go ahead and pause the video now and try that on your own, and then restart the video and I'll go through the answers. Okay, hopefully you got most of this filled in, but let's talk about what we've got here. So the first polynomial is odd. It's a degree of 7. So the degree on this is 7. It's an odd degree. The leading coefficient is a 4. That's the number glued to the front of the highest power in the list. When we have an odd degree, a positive leading coefficient, we know the ends act like a climbing line, right? Odds, they don't match on the ends, and the way they don't match on the ends is like a climbing line because it's a positive slope or leading coefficient. So that's why the shape looks like it is. I just counted the number of turns. I counted 6 turns to make a degree of 7, And that I actually sketched the ends before I sketched the turns in the middle, just so that I could get my head in the game on the end behavior. On the second one, we have an even degree. The highest power listed is a 6, so that's an even number, and it has a negative leading coefficient. When I have even degrees, my ends match. In this case, they match down, down, because the leading coefficient is negative. And again, I just sketched my little blue arrows first to show down, down, and then I filled in the middle with the number of turns to make it the right degree. The purple one is again an even degree. It's a power of 6 again, but this time the leading coefficient is positive. It's a positive 4. So I made my little end arrows point up, up, and then I counted the number of turns I needed to make sure that it was the right power, the right degree. On the last one, we threw a little curveball for you a little bit. We had the terms in the wrong order. That's why the instructions included, please make sure you put them in standard form or the right order. So the proper order of this is negative 2x to the 5th and so on. That means the degree of this is a degree of 5. That's the highest power in the list, so a degree of 5. And the number glued to that x to the 5th power is a negative number. So we've got an odd degree, a negative leading coefficient. The ends do not match. The way they don't match is like a falling line on the ends, and I just counted the number of turns to make sure that it was a 5th degree in the middle. Okay? If any of that went too fast, go ahead and pause and try it again and replay. Now let's talk about multiplicity. Multiplicity is something that describes an individual root of a polynomial. And roots, of course, are found at the x-axis. Roots and zeros at the x-axis. So here's a root here and here's a root here. Basically, how is the graph interacting with the x-axis? Now, the way we tell if a multiplicity is even or odd. Now remember, multiplicity is not degree. Multiplicity has something to do with the roots individually on their own. Degree describes the entire polynomial. Okay? So the multiplicity of these roots, in order to tell what kind of multiplicity, odd or even, we look at how that graph is interacting with the x-axis. If it is cutting straight through the axis and continuing in the other direction, we have an odd multiplicity. So the root A has odd multiplicity because it cuts through the axis and continues following the same direction. Even multiplicities, the way the graph interacts at the x-axis for an even multiplicity root, is that it does not cross the x-axis, it sort of bounces off of it or makes a U-turn. So we know that root B of this graph, whatever that number is, has an even multiplicity, typically 2. It could be a multiplicity of 2 or 4 or 6 or 8. Roots with odd multiplicities have multiplicities of 1 or 3 or 5 or 7. If you have a root r, the factor that goes with that root is x minus r. We learned that before. Let's see how this plays out in the chart. So we've got some examples here, and we put them in intercept form to make it a little clearer. So before we were talking about standard form, now we'll talk about intercept form, and that is the form that I asked you to do in your project. When we had the project polynomials, I asked you to put them into Desmos in intercept form so we could clearly see what those roots were. So if I look at this first polynomial, I notice that there are 2 roots shown, right here and right here. The factor x minus 1 causes a root 1. The factor x minus 3 causes a root 3. So this graph is interacting at the x-axis at 1 and 3. The multiplicity of each of these roots. The multiplicity of the root 1 is a multiplicity of 2. And the multiplicity of root 3 has a multiplicity of 1. That little invisible power of 1 means it has a multiplicity of 1. The degree of this polynomial, if we weren't putting it into our calculator to look and count the terms, we could actually do it quickly here by adding the multiplicities. The degree of this polynomial is 2 plus 1. We can add the multiplicities of those roots. Let's think about what these look like at the axis. Are they a cross at the x-axis, or are they a bounce at the x-axis? Well, the first root, root 1, has a multiplicity of 2, so it must be a bounce. It's an even multiplicity, so it must be a bounce. It doesn't cross through. But the root 1, the root of 1, has a power of 1. The root of 3 has a power of 1. That's an odd multiplicity. So it doesn't bounce, it crosses. Let's do another one. Let's list the roots first. The root that's caused by this factor is -2. The multiplicity of this is 2. The action that happens at the x-axis for that is a bounce. It's an even multiplicity, so it's causing a bounce. Let's look at the second one. The factor of x minus 3 causes a root of 3. This particular factor has a power of 2, so the multiplicity of the root 3 is 2. Once again, that's an even number, so it must be bouncing there. The total degree of this polynomial is the sum of the multiplicities. 2 plus 2 is 4. Let's do another one. Now this is interesting. We actually have 3 roots. Did you see what I just did there? This guy right here is a third root. So let's talk about that one first. This root, technically we could write it as x minus 0, right? That's what's happening there. So we have a root at 0. That root has an invisible power of 1, so its multiplicity is 1. And if it's an odd multiplicity, it must be crossing at that location. It must be crossing at 0. Next one. A factor of x minus 3 causes a root of 3. This particular root of 3 has an invisible power of 1, so its multiplicity is 1. Odd roots cross at the x-axis. Last one. We have a multiplicity, we have a root of -2 being caused by this factor of x plus 2. That root of -2 has a factor that's being brought to the third power, so the multiplicity on that root is 3. And since it's odd, it's a cross. It's going to cross through the axis. To find the degree of this polynomial without plugging it into the calculator or Desmos, I can add the multiplicities of these roots. The degree of this polynomial is 5. Let's talk about, and so you will see this play out. I would definitely play with these. I would put them into Desmos. These are great examples to put into Desmos to see how these play out at the axis. Cut-throughs, like I said back here, cut-throughs will cut straight through the axis. That's a multiplicity of 1. That factor must have had a power of 1 at it. This one bounces off of it, so whatever this is, whatever factor caused this must have had a power of 2. Let me show you what a power of 3 or a multiplicity of 3 looks like. It still goes through the axis, but it kind of sits there for a little while. So that's how multiplicity of 3 acts. Of course, it could also act like this, right? Just like these multiplicities of 2, they might not bounce from the top down, they might bounce from the bottom up, right? So start playing with Desmos and your graphing calculator to see how these factors of various powers act. And this is how this is what you should be able to identify off of the graphs for your assessment. The last thing we talked about in this project, domain and range and inequality notation, mostly because A, we needed to review it, and B, Desmos needs to see inequality notation if you want to cut a graph off. So let's remind ourselves, if we had a graph that looked like this, actually, I don't want it to go on forever. So we had limited our domains and ranges to make these graphs only exist within our pictures. And so when we have a graph that looks like this, let's call this So if you had a graph like this, let's remind ourselves what the domain and range were. Typically we like writing in interval notation, but like I said, Desmos likes inequality notation, and it was a great opportunity to practice this. So the domain and range for inequality notation is written like this. The domain is written like this, and the range is written like this. This is review, so this is really just review. And so we just need to find the values that go here, that bound these functions. So domain, of course, it's x values, so we look left to right and count how wide this function is. This function goes all the way down to -4 and up to +4, right? It stops here and here. So the domain of this is -4 is less than x is less than 4. That's how you would state the domain in inequality notation for Desmos. And then the range, of course, is y values only. Y values are listed bottom to top. So the lowest y value to the highest y value, -1, 2, 3, 4, 5, 6. So it looks like -6 is the lowest y value, and the highest appears to be 4. Okay, so be sure that you practice that as well. That is exactly how Desmos needed to see it, and we needed to practice writing inequality notation anyway. Domain is always x values, our range is always y values. Now, you have a page of independent practice that must be completed in order to qualify for retake or to get you ready for the assessment. So go ahead and attempt that, attempt all parts of that, and review these notes with your teacher. If you have listened to this entire video, I would go back and put a big circle around your name. Go ahead and circle your name. If you've had the sound on the whole time for this video, circle your name. And that is all. Good luck on your assessment.